Good morning, everybody. I hope that you guys are doing well. Um, I've got the captions working, so that's a go. I'm starting to record. Um, let's see, what else do we have? Um, I think those are the big things that I wanted to talk about. Um, and I'm sorry for being late on posting the PowerPoint, but that is up as a PowerPoint and as a PDF. There were a couple of items that I wanted to address right off the bat, so I'm going to share my screen so I can write. And if anyone has any questions, we'll jump. We'll. I'll be happy to field those. And you can add them to the chat, or you can unmute yourself and speak. Okay, so right, today what we're going to do is kind of a chemistry overview. And these are really getting on the high points of what we'll need for this class. Because we're kind of, you took Chem 1310, and in 1310, you talked about the periodic table, you talked about gases and the gas laws and physical properties, chemical properties. And in this class, what we're going to do is we're going to kind of take the big umbrella of chemistry and we're going to say, we're most interested in the chemistry of living things. And specifically, we're most interested in drugs and cancer and drug design, the process. And so, a fair question, an important question is, do we need to know everything? And are we going to be using lots of information from like gases and calculating pressures? We're not. Does that mean we can completely forget it and neglect it? No. But what's most important for this class is to understand a couple of fundamentals about bonding and basically kind of properties of elements. So, what we're going to be doing today is going through a little bit of a review so that then we're kind of setting the stage to talk about organic chemistry. And then that sets the stage for talking about biochemistry and biological molecules. Now, with that in mind, see a chat item. Oh, good morning. Um, so what I wanted to mention was what is currently on Canvas. You've got the Proctorio practice quiz. That Proctorio practice quiz is most or more than anything else, it's answering the question, does Proctorio work for you? And if the answer is yes, fantastic. A sign that Proctorio is not working for you is if you get prompted for an access code. If you are prompted for an access code, that means that Proctorio, which is a browser extension, is not opening. And that could be a number of reasons. It could be um, an outdated operating system. It could be an outdated browser. It could also be a pop-up blocker. So, in the event that you're trying to take that Proctorio practice quiz and you get notification, oh, well, enter your access code. You do not have an access code because Proctorio enters that access code for you. So if you're prompted, hey, what's the access code? That means that you've got possibly a pop-up blocker, a browser issue, or an outdated operating system. Let me be clear though, of the, let's see, last semester I had 150 people, 150 people in 1310, 30 people in 1330, 70 people in 4375. And I'm not saying these numbers to like flex or anything. I'm just kind of putting them together. And then I had about 70 people over the course of the summer. So that would be 250. I'm going to say around 350 people. This outdated operating system was an issue for one out of 350. So that's not exactly the most common issue. The most common issue is the browser. It's a browser or a pop-up blocker combination. So when you get prompted for access code, or if you get prompted for an access code, well, then if you can turn off your pop-up blocker, try doing that, try disabling it, and then try going back. Um, Now, granted, a pop-up blocker is kind of a security thing, so you probably want that engaged. Um, you want that engaged when you're regularly just on the internet, so you're not bombarded with 500 pop-ups. Um, an alternative to that is I use Google Chrome, and that's kind of my default browser. If there was something like if I encountered this issue and I found that, oh, it was the pop-up blocker issue, and I was like, ooh, I don't really want to turn the pop-up blocker off. Oh, I'll use Microsoft Edge or I'll use Mozilla Firefox. I'll use another browser to see if that will work with Proctorio. Um, so if you're prompted for an access code, I would say first, look at my pop-up blocker. Second, try a different browser. And then third, you might want to check your operating system. And the one person who encountered this issue had a MacBook Pro that was like 8 years old. Um, if computers aren't exactly your thing, of course, to navigate all these things, you can always contact ITAC at txstate.edu. Now, in the event that you encounter these issues and you email me, well, then I'm not in like a belligerent way, but I'm just going to ask, did you go through this process? Did you go through these steps? Did you try pop-up blocker? Did you look at a different browser? Did you look at your OS? Um, and that's just because that's my level of knowledge on navigating computer software issues. So that's kind of where I'm gonna, beyond that, I'm not going to be too much of a help. I don't mind jumping onto a Zoom with you and trying to help you work through it, but iTac is very helpful. But I would, from my experience, browser is the issue about 95% of the time. Um, the other issues are I think I don't know if it's a Chromebook or exactly um, one of those computers, either a Chromebook or maybe like a Microsoft Flipbook or whatever those are called. I don't know what they're called. I'm gonna go with Flipbook though, because that sounds good. Um, those are the ones that you want to that you might encounter an issue with. So I would, just be ready to contact ITAC at txstate.edu. With all of that said, most folks don't have an issue. I just like to try to get ahead of this so that you can take care of it. Now, this Proctorio practice quiz, this closes at Sunday, or sorry, on Sunday, the 19th at 11 p.m. Not 11:59, not 11:30, not at midnight, 11 p.m. It's done at 11 p.m. If you are taking that practice quiz at 11 p.m., then it will cut you off. Um, and remember, it's one question. So just jump in there and do it. And if you do it, I'll give you bonus points. It's 2 bonus points on the final. You'll see on your grade book or in the grade book, it pops up as nothing out of zero. But that's just the way that you make a bonus point or you make a question worth bonus points. Okay. In addition to that, at this point in time, there are 3 quizzes that are up. Those 3 quizzes, 5 questions each, open book. I'm going to say open book/notes. work with peers, um, closed AI, and um, no cheating. And whenever I say no cheating, I don't want you to think like, well, that doesn't make any sense. No cheating, but I can work with my friends. Yeah, you can. I have no problem with you working with your friends. But working with your friends, or to me, what does if there's a group me, which I don't know if anyone started a group me. If you have, fantastic. If you haven't, maybe start a group me. Um, what I consider to be cheating is somebody getting on a group me and saying, the answer to question one is B, two is C, three is D, four is five, or four is A, and six is, sorry, five is B. That's cheating. That's what I don't want. I don't mind if you jump into the group me and say, "Hey, I'm having trouble with this," and then say, "Oh, well, did you look at slide number 5 on the PowerPoint?" That's a good place to look. Or look back at your 1310 notes. I'm not a lot of stuff is going to come from your 1310 notes that will not be covered in my PowerPoints. But that's where I'm going. And no, I don't want you to use Gemini or College Tools or any other browser extension AI to answer these questions. I want you to look through your stuff, review the PowerPoints, review the videos. Those 3 quizzes are up. They're 5 questions each. They are due at 11 p.m. Sunday, the 19th at 11 p.m. Um, and you have 2 tries, 2 attempts each. Now, the reason that you have 2 attempts is because what I want you to do when you're doing these quizzes is to, and each one, sorry, last thing about them is you have 15-minute timer. I want you to open the quiz and read the question and say, oh, well, this is about electronegativity. Okay, the answers are A, B, C, D. I think the answer is A, fluorine. So I'm going to mark that on my first attempt. First attempt, I see I marked fluorine. Okay. Um, 2, 3, 4, 5. Question 2, I marked B, which was blah. And it's good to record. And you can do screenshots, whatever you want. B, I marked, let's see, C, not C, sodium. Record what you answered. You're not going to get direct feedback that says question number 1 was right, 2 was wrong, 3 was wrong, 4 was wrong, 5 was right. Instead, you're going to get a score. You can look at the grade book and see, oh, well, I got 4 out of 10. Okay. Which ones, this is where I want you to use your critical thinking skills to say, okay, well, which one did I think that I got right? Because question number 1, the question was, which is the most electronegative element? I'm looking at my notes, fluorine. That one's gotta be right. Okay, so now question number 2. Okay, the question was, this is a non-metal. I answered sodium. The other answer options were blah. I don't think I got that one right. So now the next time that I take it, I'm going to try something else. Okay. Now, with that said, I strongly encourage you to take screenshots of the answers that you submit. So then you can look at your score and then try it again. That's the point of the multiple attempts. So you can kind of learn from and deduce what things you got right and what things you did not get right. You have 15 minutes. You can work with your peers. It's open book and open notes. Closed AI, no cheating. Um, yeah, quizzes on a week-to-week basis. They go up on Mondays and they close Sundays. The other thing that we have as a graded item are, sorry, are activities and quizzes. You're going to have typically three per week, and they're going to cover the content for that week. Activities, these will go up on Mondays and close on Sundays also. They have to be submitted by, or they have to be submitted by 11 p.m. on Sundays. And then there's a little bit of you can, sorry, you can submit it late, but you do lose a little bit of points. Do the quizzes have to be done in one sitting per attempt? If first attempt is better than the second. Okay, so um, if you do one attempt, that would be in one sitting because you have the time limit. I think that's the best answer for that. Do the quizzes have to be done in one sitting per attempt? If the first attempt is better than the second, the best score is saved. I hope that I answered your question, Stanley. Now I'm moving on to Marcus. If I didn't, Stanley, feel free to add. Can we use our notes on our laptop, or do you recommend using a notebook? Whatever vehicle you find best to take notes. Screenshots are super fast. I use the print screen um, function on my keyboard, and I have there's a piece of software that just allows me to copy and or click and drag and then copy into a Word document. So that's how I do it, and then I'll kind of scratch that up. I'll print that up or write it on it in a PDF. So either way is fine. You can use your laptop. Sorry, can we use our notes on our laptop? Yes. Do I recommend using a notebook? It's your call on that one. Do you recommend doing the quizzes toward the end of the week? I think that's probably a good idea. I would say as soon as, I think what I would probably do is I would do them on, after Wednesday or something. Um, Snipping. Yes, the snip tool. That's what it is. Thank you, Javier. Yeah, I love that tool because it's just like click, drag, paste. It makes me feel so like savvy. Okay, activities. Oh, great question, Stanley. Will tests be similar, or will they have similar questions to the quizzes? Absolutely. So, questions that you see on quizzes, think about those. Sometimes you'll have questions on your quizzes that have a table in there. And more times than not, I'm asking you to like process that table. What I mean by that is like read the table and interpret the information on it. Um, and that brings up, okay, two things. I wanted to talk about the activities. These are going to go up on Mondays and they will also close on Sundays. There are no activities for this very first week. The ones that will go up on Monday, I'll post, and it's going to be two of them per week. Um, so if I think I might post those activities in the coming days or so, like either Thursday or Friday, tomorrow or Friday. Um, and those will be, just those will not be due the 19th. Those will be due on the 26th. And those activities you'll see them. They're homeworks basically. And then the last thing that I didn't really address, I didn't bring up, and I've been scribbling all over this, so I need to erase. So I'm sorry to follow up on Stanley's question. When you're studying for your exams, I would definitely look at my old quizzes because that's where good questions are going to come from. And I'm a big proponent of looking at a question and say, okay, well, how would I change this? Um, is the calendar accurate on how the classes are going? Because I see module 1.3 is going to be on January 22nd, but the quiz for it is due. Okay, Zachary, thank you very much for asking that. And I'm sorry for confusion on that. So the quiz 1.3 does not, I need to change my terminology. Okay, so quizzes, all of your quizzes are 1.1, 1.2, 1.3. We didn't look at section 1.1 of the textbook. I know that we have a module 1.1, so I got to change my terminology. This quiz 1.3 does not correspond to module 1.3. So thank you for bringing this up. I'm gonna change my terminology because that's where I sorry about that. Um, but the calendar is correct and the quiz due dates are correct. I just need to change what I refer to things as. Um, I might just go with modules one, two, three, all the way up to like 27 or something like that. I'll sort that out. Does that answer your question, Zachary? Okay, sorry about that. I'll get that sorted out today. Um, okay, the last thing that I wanted to mention before we jump into our material today is on your exams, you can use a 3 by 5. I always say index card, um, scratch paper for your notes. I think that some people would refer to this as a cheat sheet. What I mean is you can write on this 3 by 5 piece of paper and use that as a part, use that when you're taking your exam. You will be prompted to hold that up during the exam period and show both sides of it. You can write on both sides. So basically, you can write your notes, write important things where there's some calculations that were tough for you. You know, give yourself an example calculation. Was there a molecule that I said, oh, you got to know this one? Draw that molecule. It's whatever you want to put on there, you can put on there. But that's all. You can use blank scratch paper, for doodling when you're taking the exam and everything like that. But this will be kind of your exams will be effectively open 3 by 5 scratch papers. Does that make sense? Can I get some thumbs up for that making sense? Awesome. Okay, cool. All right. So let's go ahead and jump right in. This whole thing should look pretty familiar. The periodic table. Now, one of the most important parts about the periodic table is, screwed that up. This is 10, 11, 12. The periodic table here is divided up into a couple of different groups. Will the exam be taken on the same device that proctoring is run on? We're going to be doing proctoring with Proctorio and with Zoom. So you'll be taking the exam on the device that Proctorio is open on, but then you'll also have a second device like your phone open on Zoom. So double proctoring, basically. And I can show you some examples as we get closer, kind of what that looks like. Cool. Okay, so the periodic table, here it is. Now, whenever it comes to the organization of the periodic table, most of the stuff on the periodic table is most of it metals or non-metals. Add to the chat, what do you think it is? Got some votes for non-metals. Got some. Okay, so if you look at the periodic table, it's a little bit confusing because this group down here, your lanthanides and actinides, those fit right in here. So if we were to kind of truly draw out the periodic table, what I'm showing here is that grouping. Then we take the lanthanides and actinides, these two rows at the bottom, we plug those in. and those fit right here. And then, does anyone remember what these are known as? The group in the middle? They're a type of metal. They are your transition metals. Okay, so I'm going to put an X here to indicate this. And then our transition metals. And then last but not least, I'm going to draw a Y over the green spot because that's there. And then I'm going to do a hashtag over the transition metals, and that's right there. Now, in 1310, you probably talked, it might have been briefly, but the kind of breakup of the periodic table, and we've got this right here. It's kind of a line that goes down. I believe it goes there. Oh, dang it. There we go. That line right there separates the metals from nonmetals. Most of the things on the periodic table are actually your metals. And so everything to the left of this, metals. That stair step line there separates your metals from your nonmetals. And then everything to the right are your nonmetals. Now, in 1310, one of the things that you talk about quite often is you talk about different types of compounds, ionic compounds versus molecular compounds. And you talk about, well, a metal pairs up with a nonmetal, that makes an ionic compound. If you have two nonmetals pair up, that makes a molecular compound. Important, valuable information. Most of what we're going to talk about in this class is our molecular compounds. So that's two nonmetals coming together, or multiple nonmetals coming together. Now, if you remember this table, this shows us, or the numbering up here shows us our number of valence electrons. But over here, the number that's highlighted in yellow is the number of valence electrons. Does anyone remember, or can anyone add to the chat or unmute and say it? Which are your valence electrons? Where are those with respect to the element? Or the atom. Outermost. Perfect. Those are your outermost electrons. Those outermost electrons are the ones that kind of like are the handshakers. They're the ones who like greet other elements. So when you talk about sharing a bond or a bond between two elements or two atoms, that would be sharing of electrons. Now, with that in mind, just a second. I want to ask my first poll question. There's actually two poll questions here, so make sure that you answer them both. And just so everybody knows, I'm giving full credit for everyone for the first or for Monday and today. Monday, we didn't have any poll questions. Today is just kind of a test run with poll questions. I want to make sure that everyone's, got a sense of how it works. And maybe I know that some people might be on the mobile app, in which case getting to the poll questions is a little bit different. So I want you to kind of have a minute to try to figure that out. We got 34 people in class and 25 have, oh, there we go. I can give about 10 more seconds. Usually for questions, I'm going to give about 45 seconds to answer them. Um, so I also kind of test the waters and I'm like, ooh, well, this is a harder calculation or this is a tougher question. So I'll give a little bit more time. Today, though, I'm going to go a little bit more briskly through the questions that so. Okay, we got 31 answers. I can give her feedback, results. Yep. Charge of a proton is positive, charge of an electron is negative. So good job. Now, that's important because that's ultimately going to come into play when it comes to the overall charge of a molecule and the charge of an atom. So if we were to look at something like, this is my favorite, it's my favorite Nirvana song, but it's also like a super simple element to draw. Let's go ahead. I'm going to draw the nucleus of lithium. The lithium nucleus, in addition to having neutrons in there, it's also got three protons. I'm going to draw a box where my lithium atom is. Based on the charges that I've identified there, based on the things, the subatomic particles that I've drawn in there, what is the charge of that atom? This isn't a trick question. Count up the number of things that are there. It's positive. Now, in addition to that, take it a step further. Consider the magnitude. Brooks, fantastic. It's +3. Okay. Now I'm going to add a little bit of a wrinkle to it. Let's go ahead and say, here's an electron. Now what's my charge? Yep. And I think the rest of you guys are just like, okay, now it's gone. When I have an equal number of protons and electrons, my charge is 0. When I throw an extra electron in there, my charge is -1. So those two things have to be kind of considered with respect to one another. Now, when we talk about different compounds and different molecules, we have to be thoughtful of this. What is the number of charges that that thing has? Now, in addition to that, our Lewis structures are ways that we look at a molecule, the way that we kind of visualize something. It also gives you a sense of, from the number of valence electrons, how many bonds it likes to form. Now, I'm going to go with my second poll question here. How many bonds does carbon typically have? Or you could rephrase that as how many bonds does carbon typically make? You got two competing answers. And I think I know why one of the answers is popular. Now I've got three. So three answers have entered the chat, or three responses have entered the chat. We got 23 responses. I want to get everyone to answer this one just so then I can get confirmation that you know how to answer the question from a technical standpoint. 31. We got three more people. One left. There's one person left. One person left. I'm going to give you 10 seconds. Now I'm going to start my 10-second timer. 1, 2, 3, 4, 5. Oh, it's not going to happen. It's not going to happen. It's not going to happen. That one person did not respond. Okay, there's the results. The majority of folks picked 4. And you're right, because carbon typically is going to form 4 bonds. It likes to form 4 bonds. I'm going to close that. There we go. Now, what we've got here is carbon as a group 4 element likes to form 4 bonds. Now, I'm guessing the second most popular answer was 2, and I think I know why. I think the reason is because lots of people were probably thinking about, or the people who answered that were thinking about this molecule right here, carbon dioxide. And you know what? The Lewis structure of carbon dioxide is pretty common to look at. But how many bonds is this? That's 1 double bond, which is the same as 2 bonds. This is also 2 bonds. So that's 4 bonds, but it's also 2 double bonds. So I think that's probably where the people who selected 2, where they kind of got mixed up. Now, these structures are important to know. The ones that are maybe the most important to know are these right here: carbon, nitrogen, oxygen, and one other one, hydrogen. Hydrogen likes to form one bond. An example of a very happy molecule is this right here, CH4. This is methane. Each hydrogen has one bond. Each carbon has, or the single carbon has four bonds. Okay, so carbon's happy, hydrogen's happy. We've got electrons shared between the two of them. In addition to all this, we've got some very common ions. Now, the ones that I think are people are most familiar with, these two, or these three rows, and then these two rows. And that's kind of going to be the most important ones. Now, if we think about something like lithium, and we jog back for a second. Lithium, or let's go with sodium right here. Sodium has one valence electron. Now, when sodium loses that one valence electron, whenever it gives that electron up, well, that means it has one less electron than its number of protons. And so that has what is known as a noble gas electron configuration. That noble gas that it has the same electron configuration as is neon. So if something loses an electron, it adopts a noble gas electron configuration. Now, Cl minus. Well, if an element or if an atom has a negative charge, it's commonly known as an ion, and it's picked up an extra electron. And whenever it picks up that extra electron, it has a noble gas electron configuration. Now, with that in mind, and considering that information, be ready to add to the chat. These right here, helium is one also, but neon, argon, krypton, and xenon. These are all noble gases. We know that noble gases are very stable. There is a rule with respect to bonding and number of electrons that an atom has that a noble gas kind of displays, exemplifies, shows. I'll give you a little bit of a hint. It's a rule, and the word that comes before rule with respect to bonding starts with an O. Absolutely. The octet rule. Every atom wants to have 8 electrons around it. Noble gases, or 8 valence electrons. Noble gases, they've got 8 valence electrons. When they have those 8 valence electrons, they're happy. If we look at this molecule right here, each one of these bonds is 2 electrons. 2, 2, 2, 2. Carbon is sharing those electrons with hydrogen. So how many electrons does carbon have surrounding it? It's got 8. So our octet rule is basically that atoms tend to gain, lose, or share electrons until they have 8 valence electrons. That's the goal, 8 valence electrons. Now, what that means is that if something's on the right-hand side of the periodic table, it's more than likely going to gain electrons to get there. So it's easier for chlorine to pick up 1 and therefore have a negative charge than it is to lose 7. It makes more sense. Meanwhile, if we look at potassium, what makes more sense? For potassium to just lose 1 or to gain 7 electrons? Well, it's going to lose 1 electron and it's going to be in good shape because then it's going to have a noble gas electron configuration. Brooks, that's a fantastic question. 8 valence electrons basically is the way that an atom gets stability, gains or achieves stability. There we go. That's a good way of looking at it. Great question, Brooks. Thank you. So think about every atom as wanting to get 8 valence electrons either by sharing or gaining. Now, that brings up bonding. That brings up ionic bonding and covalent bonding. When we talk about ionic bonding, sodium chloride, table salt, that is an ionic compound. A sodium atom will lose one electron. It will give it up to chlorine. So that's how, whenever we talked about, well, chlorine wants to pick up an electron. How's it going to do it? It doesn't just pick it up from Nowheresville. It picks it up from another atom. It gains an electron from an element that wants to lose an electron. This is ionic bonding is the transfer of electrons. Now, typically, ionic bonding is going to be a metal and a nonmetal. Your ionic compounds are going to be solids at room temperatures. Covalent bonding is where atoms are sharing electrons. So here what we have is two chlorine atoms that come together to make Cl2. Those two chlorine atoms that come together to make Cl2, well, they each rolled in with 7 valence electrons. Chlorine with 7 valence electrons, chlorine with 7 valence electrons. If they share 2 of them between them, well then, what I always like to do is anyone familiar with that? It's not the MasterCard logo, but this is a type of diagram. Yeah, it's absolutely a Venn diagram. I always think about something like chlorine, Cl2, as basically being a Venn diagram. This overlapping region in the middle is 2 electrons that, well, this chlorine is going to say, hey, I've got those 2 electrons. And then this chlorine is going to say, oh, yeah, I've also got those two electrons. They are sharing them. So that gets them to have a complete octet. In this circle, there's 8 electrons. And in this circle, there's 8 electrons. We didn't make electrons show up out of nowhere, but instead by these 2 atoms sharing those electrons, well, they both achieve an octet, or a content octet. Now, covalent compounds are typically going to be gases, liquids, or solids at room temperature. Here, what we have in this chamber right here, more than likely is chlorine gas. Chlorine gas is something that people can accidentally make in cleaning situations. If I remember correctly, if you mix bleach with an acid, I think that's some of the ways that it can happen. And I think also like if you have a bleach solution that's like super old, that can also make chlorine gas. And chlorine gas it's pretty nasty, so you don't want to mess with that. You don't want to accidentally make it also, as much as you can contain accidents. So when it comes to sharing electrons, there's a phenomenon known as electronegativity. And electronegativity, I always think about it kind of like a game of tug of war. It's the ability of an atom to attract shared electrons. Now, the electronegativity that's displayed here, and these numbers are kind of small. That's 3.98. We'll go ahead and call this 4. And then down here for cesium, it's 0.79. What do you notice about those numbers across the periodic table? So do you notice anything moving, let's say from the left-hand side to the right-hand side? What do you notice about those numbers? They increase. Absolutely. Now, if I told you that on this scale, on this what's known as the Pauling scale of electronegativity, it's attributed to Linus Pauling, who won 2 Nobel Prizes, one for peace and one for chemistry. This is the Pauling scale of electronegativity. If we think about this in terms of that game of tug of war that I was saying, fluorine with an electronegativity score or measure of 3.98. Let's go with CSF. Fluorine is 4.0. Cesium, we're just going to call 0.8. The sharing of electrons that takes place between cesium and fluorine. Now, first of all, let me ask you this. How would you classify cesium? Metal or a nonmetal? Metal. Cesium on the left-hand side of the periodic table is a metal. Okay? Now on the right-hand side of the periodic table, fluorine. How would you classify fluorine? As a metal or a nonmetal? Non. Perfect. Okay? Now, let's jump back. When we look at these two types of bonds, an ionic bond or a covalent bond. An ionic bond is a metal and a nonmetal. And that is basically the transfer of electrons. So do they share them? Not really. Now, covalent bond is a nonmetal and a nonmetal. We go back over here. How would we classify CSF as a compound? Or as what type of bonding exists between cesium and fluorine? Ionic, 100%. Okay. Now, thinking about that, the electronegativity differences. We've got a 4 point. I'm going to redraw this to give myself a little bit more space. CSF. Fluorine is 4.0. Cesium is 0.8. Okay. The difference between those numbers, if you did 4.0 minus 0.8, or if you did 0.8 minus 4.0, and you use those two uprights as your absolute value, the difference between these is 3.2. Okay. Now, we a moment ago classified this as an ionic compound. And by it being an ionic compound, it's got an ionic bond. And with this being an ionic bond, this is like the transfer of electrons. Cesium gave up that electron. Fluorine said, gladly, I'll take it. I love it. It's great. Now, what do you think that means in terms of electronegativity difference and, well, yeah, electronegativity difference and that compound itself? What you can take away from that is the higher the, I'm going to use E neg difference, the less, or the, sorry, let me rephrase that. The higher, the more likely our compound has an ionic bond. Okay. Now, if we were to say, look at a different compound, F2, which is the same as fluorine going to fluorine. What's the electronegativity difference between two fluorines? 0. You're absolutely right. Okay. Now, let's imagine, and I'm going to try to personify this. Incredible Hulk. BLE. So fluorine is a our fluorine is the Incredible Hulk, and cesium is not the Incredible Hulk. Incredible Hulk's stronger than everyone. So let's just go with I can't think of a comic book character who's particularly weak. It doesn't really make for a very exciting comic book character. Hawkeye, perfect. All he does is shoot 5 arrows and then he's done. So we've got the Incredible Hulk and Hawkeye. The Incredible Hulk is very strong. The Incredible Hulk basically walks up to Hawkeye. The fluorine walks up to Hawkeye. The fluorine walks up to cesium and says, "Hey, I need an electron." And Hawkeye's like, "Oh, great, let's share it." And then the Incredible Hulk is like, "You can say we're sharing it, but it's mine." And Hawkeye's like, "Yeah, yeah, that's kind of what I meant. Yeah, that's what I meant." So the sharing that takes place in an ionic compound is basically none. And we have a definition for that. So when we have an electronegativity difference of greater than 2.0, we classify that compound as ionic. Now, when the electronegativity difference is less than 2.0, well, we have, or we classify that bond as being a polar bond. The electrons are being shared, but they're closer to one of the elements. So bonding electrons are shared, but unequally. Okay, so this would be like a polar covalent bond would be like Hulk and Thor. So the Hulk would be fluorine, and then let's go with Thor would be nitrogen. Electrons are being shared, but which one of these two um, elements or which one of these two atoms pulls with greater force? Well, that would be the Hulk. The Hulk is stronger. The Hulk has a greater electronegativity. Nitrogen has a lower grade. Brooks, absolutely. So that's where we've got this kind of difference in designation. So all of these right here, HF 2.1 and 4.0, our difference there is an absolute value. So you could say 2.1 minus 4.0, and that's going to be negative 1.9, but it's an absolute value, so it's 1.9. CF, well, 2.5 and 4.0. The difference there is 1.5. N and H, 3.0 and 2.1. The difference is 0.9. That is within the range of 0.5 and 2.0. So we have this kind of graduated scale, or we have this scale of how much electrons are being shared. If the electronegativity difference between the two elements is less than 0.5, those electrons are effectively being shared equally. Now, an example of that would be something like, well, H2. What's our electronegativity difference there? 0. That's a non-polar covalent bond. Let's go with they get kind of fuzzy. Okay, yeah. CH, a carbon-hydrogen bond. What's our electronegativity difference there? 0.4. So bonds are going to be polar or nonpolar. A nonpolar bond, each atom in that bond has an equal kind of claim to those electrons. A polar bond, well, one of them wants them a little bit more, so one of them is able to say that. And then the way that I always try to phrase it is that sometimes a bond is so polar, it is ionic. So it's almost like this is a step beyond polar, or ionic is a step beyond polar. Because not only are the electrons not being shared equally, but one of those elements has basically said, I don't need them. Now, with that said, I want you to know these definitions. I want you to know these ranges. A question on an exam might be something like, here is the table. Classify this bond. Is it ionic? Is it polar? Is it nonpolar? And just so you know, I'm not going to pick anything, well, or just so you know, we have our definitions 0.5 to 2.0. If it's less than 0.5, it's nonpolar. If it's greater than 2.0, it's ionic. I know that that zero point 0.5, sometimes people are like, oh, but what if it's exactly 0.5? Well, this is then a polar covalent bond. How do you get the electronegativity? Marcus, that's a fantastic question. So what we do is I'm going to go back to this nitrogen and fluorine example with Thor and the Hulk. So what I'm going to do is I'm just going to write underneath nitrogen the 3.0. That's my electronegativity. That's basically a measure of how much does nitrogen want electrons when it's sharing. Then for fluorine, it's 4.0. So the way that, okay, let me add one detail. These values will never be negative. So one way that you can make sure that they're never negative is by taking the larger number, 4.0, and subtracting the lower or the smaller number, which is 3.0 in this case. So our electronegativity difference there is 1. An alternative to that is, well, you just take the numbers. 3.0 minus 4.0, and then it maybe has been a minute since you've seen these, but when you throw these kind of two uprights, those two lines, what that means is absolute value. So if you did 3.0, if you plugged in 3.0 minus 4, then your calculator would spit out, oh, well, that's -1. But by having these uprights there, that makes a negative value or a negative result positive. So if you plugged in 3.0 minus 4.0, yeah, that's -1. But because you've got those uprights, well, then it's going to be positive. It's going to be 1. Does that make sense, Marcus? Awesome. Awesome. Okay. So now the way that electronegativity is kind of shown is we have what are known as partial charges. So a Lewis structure for HF looks like this. These are lone pairs of electrons. Fluorine has 3 lone pairs of electrons, and then right here, it's sharing electrons. Now, what do we know that we already answered as our one of our poll questions? What do we know about the charge of an electron? Well, an electron's negative. Okay. So between hydrogen and fluorine, where are there more electrons? By the hydrogen or by the fluorine? By the fluorine. Absolutely. Okay. So you could kind of look at this and just say there's lots of electrons, lots of electrons. And if each one of those electrons is negative, well, another way of putting this is lots of negatives. Another way to phrase that is you could say that this side where the hydrogen is, it's relatively positive. And the reason that you would say it's relatively positive is because in that word relative, we're doing a comparison. Fluorine is therefore, since the hydrogen is relatively positive, the fluorine is relatively negative. Can I get a thumbs up if that makes sense? Awesome. Awesome. Great. Okay. So whenever we put that together, this symbol right here, it kind of looks like a snake. That's the, if I remember correctly, it's delta, the lowercase delta symbol, or it's lowercase sigma. I get those two mixed up. But that symbol right there is a way of saying relatively, or it's another way of saying partial. Between these two, one side is going to be partially positive and the other side is going to be partially negative. So you could say that the hydrogen has partial positive. Then the fluorine is partial negative. So anytime you see this, anytime you see that S that's kind of gone a little bit haywire, if it's partial positive, or if there's that haywire S and a positive, that means partial positive, partial negative. Now, if you look at this model right here, well, we've got this half that is kind of, well, it's kind of more, it's larger. This is showing where electrons are. Where are there more electrons? On the right side, more electrons. This is kind of known as an electron density map because less electrons. More electrons on one side than on the other. More of the electrons, given the opportunity, think about this as this is Hulk and this is Hawkeye. Thank you very much. I think that was what's it? Sorry, Chris. Thank you very much for Hawkeye. That helps out a whole lot. It's the rare comic book character who's not super strong. Um, Stronger than me, maybe, probably. He's a superhero, and he's not real, so of course. Um, okay, so that's how we model that. Now, this is known as, or this is a way of looking at a molecule and depicting it and drawing it as being polar. It has one pole, like a North Pole, South Pole. It has a negative pole versus a positive pole. So understanding that's going to be really helpful for looking at molecules. Now, we've just got a couple more slides left, but the Lewis structures for atoms also kind of look like this. Now, if we look at a water molecule, one thing that I want you to recognize is it's got two lone pairs of electrons. So if I were to draw this and this, okay, so partial positive, partial negative. We're talking about the entire molecule. Would I put the partial positive by the hydrogen or the oxygen? Add that to the chat. Hydrogen. Perfect, Chris. And then our oxygen is going to get that partial negative. Ammonia. Well, partial negative. And then each one of these guys is going to have a partial positive. And when you have that separation of kind of charges and density of electrons, you're going to have things that will kind of attract to one another. This part right here, That partial negative charge. What do you think that's going to be attracted to? Partial negatives or partial positives or full on positives? What do you think? Partial positives. You're absolutely right. These are opposites that attract one another. So now let's say I'm going to try to draw a connection here. Okay, so I want you guys to all agree that water is a polar molecule. Molecule. There we go. Because it's got a partial negative and a partial positive charge. Okay, and now I'm going to draw another molecule. It's a great question, Stanley. So the partial positives just have to do with the separations and the differences in the electronegativities. If the more electronegative element, the more electronegative element is more negative. So it gets the negative, or I'm going to say gets the negative slash partial negative charge. And if you're looking at this and you're thinking, well, where am I getting that from? Here are the numbers. Here are the electronegativity values. The ones that have the decimal, so 3.0, 3.5, 4.0, and so on, are all different electronegativity values. So whenever I was looking at a water molecule, oxygen 3.5 and hydrogen 2.1. Okay, so that's first. Now, Zachary, couldn't you draw these Lewis structures in different ways that would change the poles? Well, in some instances, potentially. Um, so I know that in 1310, you probably talked just a little bit about drawing a molecule in lots of different ways. So I'll use, if it's okay with you guys, I'll use CO2, carbon dioxide. Now, if you follow the rules for drawing a Lewis structure, you can end up with a couple of different examples of carbon dioxide. There's CO2, one depiction of it. Another would be like this. Is that kind of what you're getting at, Zachary? Okay. So it's a fantastic question. Um, because yeah, I've got my two different models for carbon dioxide, A and B. And when you look at A and B, I mean, we've got this oxygen right here. How many electrons is it sharing? It's sharing two. It's got 6 electrons to itself. So really, in this depiction, this side is negative, and then this side is relatively positive by comparison because it's sharing electrons. Let me. So we've got that big separation there. Now, where it gets a little bit complicated is the rules for drawing Lewis structures. There's like 5 rules, 5 basic rules, and then after those basic rules, it pivots and it's like, okay, you've looked at the basic rules. Now here's a rule to follow this rule to follow this rule. And so when you do that, when you follow like the next tier rules, this structure right here gets eliminated. So this structure right here is invalid because of the fact that if you have, or Brooks, I'm going to get to that in just a second. That's a great question. Um, the reason for this is because the Lewis structure is more accurate of what is actually taking place when those two electronegative elements, those two oxygens, are both negative. So oxygen doesn't like to have even a partial positive charge, so it's going to reject that. Now, that's just one example. To your question of can you draw any number of molecules where the poles change? Yes, absolutely. And that's a fantastic question. I hope that answers you. Now, Brooks, I'm going to go on to you and your question. Can the molecule be a neutral? And Zachary, if you have any follow-ups, please don't hesitate. But to answer, sorry, let me answer your question, Zachary. Couldn't you draw these Lewis structures? Yes. It depends on if that reflects what the molecule actually looks like, though. In some instances, yes, you can draw it in a different way and it looks that way, and that's realistic. In others, not quite. So my answer to your question is yes and no. Okay, now, Brooks, can a molecule be neutral? Absolutely. I'm going to show you one. CH4. Okay. Now, if we're thinking about the electronegativities of hydrogen, hydrogen is 2.1. Carbon is 2.5. Okay. So 2.5 minus 2.1. Our difference there is 0.4. What do we know about the bond if our electronegativity difference is less than 0.5? It's nonpolar covalent. Perfect, Chris. Well done. So this bond right here, well, it's nonpolar covalent. There's not a pole. So what that means is that there is no partial negative charge here. There is no partial positive charge here. So carbon isn't partially positive or partially negative. Hydrogen isn't partially positive or partially negative. This molecule is known as a non-polar molecule because it has nothing but non-polar bonds. Now, with that in mind, if this molecule right here comes in close proximity to water, what do you think? If you had one non-polar molecule and one polar molecule, do you think those two are going to mix up well? When you think about like dissolves, Chris, absolutely. They won't mix because they have different properties. A polar molecule loves to mix up with other polar molecules. A non-polar molecule loves to mix up with other non-polar molecules. If you take a non-polar and a polar, they're just kind of like, whatever, don't care. I have nothing in common with you. Oh, you're looking for a partial positive charge because you have a partial negative region? Fine. I have no partial positives and no partial negatives. Now, that's kind of the important takeaway. You maybe remember from 1310, there were different types of interactions, and one was called an induced dipole or kind of induced polarity. That's not really something we're going to worry about so much, but being able to identify a polar and a nonpolar bond, being able to identify a bond as being so polar that it's ionic is also helpful. Does anyone have any questions about this before I proceed? Okay. If you do, go ahead and add them to the chat or unmute yourself. I'm going to move forward, and I don't mind coming back. Um, Here what we have is number of covalent bonds formed by elements. Well, one way you could think about this is if something has 7 valence electrons, it wants to form one bond. If something has 6 valence electrons, it wants to form 2 bonds. Something has 5 valence electrons, it wants to form 1, 2, 3 bonds. It wants to find 3 places or 3 electrons that it can share. Carbon wants to form 4 bonds. Now, those bonds could be a triple bond and a single bond. It could be 2 double bonds. It could be two singles, and one double. It could be most common, four single bonds. So lots of what we need to know for this class in order to kind of get a good sense of things is think about where electrons are. Think about valence electrons and think about numbers of bonds that different elements want to form. If you understand number of bonds that an element likes to form, you're going to be in really good shape for this class. So this right here and this right here, these are going to be very helpful as we proceed through this class. Um, like I said, I want you to know these definitions: nonpolar covalent, polar covalent, and then so polar that it's ionic. The last two slides have to do with nomenclature. And I'm not going to ask you explicit questions about nomenclature, like what is this compound, but there will be times whenever I say a phosphate ion. And I want you to be able to, like, you have some context. Like, now I'm saying a phosphate ion is phosphorus and four oxygens with a -3 charge. Do you have to know what that looks like? Not right now. Um, I just want you to kind of know these things so as we proceed through the class, you're like, I remember that. Do all of your notations get saved for us to view? I will absolutely save those. Um, so with that in mind, um, one, thank you guys for coming to class. I hope you guys have a great day. I hope you enjoy your long weekend. We will not meet again until 1 week from today, which is Wednesday, the 22nd. Um, Other than that, though, I'm going to stop my recording.